Hello everyone. Let me walk you through the lab for this week. We're going to be investigating pendulums. We're going to use this simulation. We're going to time how long it takes for one full oscillation, or also known as the period of the pendulum. And we're going to do that for different lengths of the pendulum. So here, zero point 0.2 meters, zero point 0.3 meters, and so on. And we're going to time the period for each of those. Now, our goal is to eventually get the acceleration of gravity from this pendulum experiment. But how are we going to do that? Well, like always, we're going to use a plot, and we're always going to start with a physics equation. Here, this is the equation for the period of the pendulum. T equals 2 pi squared L over g, where T is the period of the pendulum, L is the length of the pendulum, and g is the gravity on a planet. Now, for the data I have here, I did it on Earth, but you're going to do it for an unknown planet X. So you're going to calculate the acceleration of gravity on this unknown planet. So we need to linearize this. And as you can see in this equation here, we have a square root. Well, y equals mx plus b does not have a square root in it. So the first thing we're going to do is we're going to be squaring both sides, arriving at this equation here. So t squared equals 4 pi squared times L over g. So this used to be square root, but now we've squared both sides, so now it's gone. And I'm going to rearrange this just a little bit to help us see the y equals mx plus b. So I brought the g over to this term, and I put the parentheses there, and brought the L here. So hopefully you can see the y equals mx plus b. So you can see that the t squared is in the y position. So in our y-axis data, let's plot t squared. And in the x position, we have L. So L data is in the x position, so we'll plot L on the x-axis. And then this whole term, 4 pi squared over g, is our expected value for slope, and 0 is our expected value for our y-intercept. Now listen, we don't have t squared data. All we have is period data. So after you get your period from your experiment, you need to plug it into your calculator and calculate t squared. So 0.91 squared is 0.83, 1.05 squared is 1.1, and so on. So you're going to have to calculate what that t squared is. And this is the values you're going to plug into Desmos in order to plot, in order to eventually calculate what g is going to be. So again, by plotting L on the x-axis and period squared on the y-axis, our experimental value for slope is 4 pi squared over g, and our expected value for the y-intercept is 0. So we're going to do that experiment. We're going to take all of our data and plug it into Desmos. So again, on the x-axis is L, and the y-axis is t squared. So for L, we have 0.2, 0.3, 0.4, and so on here. And on the y-axis, we have t squared, so 0.83, 1.1, and so on. So please be careful. Don't use your period data. We're plotting t squared here. And from our Desmos, it'll tell us the best fit line of the slope, which is 4.47, as well as the intercept, negative 0.132. But how are we going to get the acceleration of gravity from the slope and y-intercept data? Well, we know that from the way we plotted it, the slope is 4 pi squared over g. So that's what we expect it to be. So m, which is the 4.47, equals 4 pi squared over g. So we can just solve for g. So let's multiply g to both sides and then divide by m, and we arrive at this equation. And we can plug in our values here. We know what 4 pi squared is, and our m value is the 4.47. We can plug those in and evaluate, and we get a g value of 8.83 meters per second squared. Now, this isn't the 9.8 that we expected, and that's fine, because in the simulation, we're going to be manually using a stopwatch to calculate the period of the pendulum. And because of that, there's uncertainty involved, and that uncertainty is going to give us a different value than the expected value that other experimenters have gotten, and that's fine. In fact, that's expected. Similarly, for the y-intercept, we expect it to be 0, but it's not, and that's okay, because we have some uncertainty in our measurement. So this lab is going to be 3 steps. We're going to be acquiring the data for different lengths. So we're going to acquire the period data for a number of different lengths here. And I'll show you that in a minute. Then we're going to plot our data in Desmos. So L on the x-axis and t squared on the y-axis. And then from that, we can calculate g from our experimental value for the slope. And then we're going to answer some questions in the lab assignment module, okay? Well, let me walk you through the lab now. So when you go to the link, you're going to arrive here. We're going to click on the leftmost one. And there's a number of things we're going to be changing here. The first thing we're going to change is we're going to be changing from Earth to planet X. This is this unknown planet that we're going to be calculating the acceleration of gravity on. So our g value is not going to be 9.8. It's going to be some unknown value that we have. The next thing we're going to do is we're going to click on the bottom left here to the stopwatch. And I'm going to drag that a little bit closer. So you can click this button to start, this button to stop, and then this button to go back to redo. And then let me show you how you're going to calculate the period here. We can click and drag on this, and we're going to drag it all the way up to 10 degrees. Do you see in the top left how the number's changing? We're going to drag that to 10 degrees and then let it go. Now, to reduce the uncertainty in our calculation, we're going to measure the time of 10 periods and then divide that by 10 to get the time of 1 period. So let's go ahead and do that now. So when it gets to the far left, I'm going to click the stopwatch and say 0 and then count to 10. So here we go. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So I have 13.93 is the time of 10 oscillations or 10 periods. So in order to get the time of one oscillation, I can just divide that by 10. So for one oscillation, we're going to get 1.393. And then we're going to plug our period into Desmos, but we got to be careful here because we're not using the period of one oscillation. We're using the period of 10 oscillations. We're using the period of one oscillation. So we have to square this value. So I'm going to get my calculator out. I'm going to type in 1.393 squared gives me 1.94. So if we look over here on the top right, our length is 0.7 meters. So when we go here to our length, which is our x-axis of 0.7, we're going to type in the 1.94 value. And then we'll change the length to 0.6 and measure the period and square it and so on to get all of our data. And then it'll tell us what our slope and our y-intercept is going to be. Okay, so to change the length, I can just click on this and drag it to 0.6. And then you're going to redo this calculation. You restart, you're going to go to 0, and then you're going to calculate 10 oscillations, divide that number by 10, square that value, plug it into Desmos for 0.6, and so on. Now, once you've done that, there are a couple other questions I'm going to be asking in the lab. And one of them is we're going to be changing the mass. So I'm going to go ahead and go back to 0.7, and then let's take this to 10 degrees like we did before. And I'm going to change my mass down here to 0.5. And then you're going to measure the period of this. So you can change the mass here. But be sure when you're doing your experiment here that you leave the mass at 1 kilogram, okay? The other thing, let's go back to 1 kilogram. And we're going to change our amplitude here all the way to 90 degrees. And you're going to be measuring the period of this and answering some questions about that as well. All right, let's get to it.